their room, so don't forget to take them on your way out. And our next speaker will be talking about something completely different. So far we've, had presentations on more traditional by now way of doing, big data, HPC, data science. This is actually something completely different. This is in Rust, and this is, Dataflow. So with that, take it away.
Excellent, thank you. So I have the mic switched off mute. Right, so as mentioned, this is going to be totally different. I'm not going to use Java anywhere. There's going to be no Apache anything. We're going to look a bit at some issues. I should say also, before starting, I gave this warning yesterday. This is all open source research, I would say. So the problems I'm trying to solve are more of these scientific inquiry problems, rather than how can I make your life easier with respect to the software stack you're currently using. So if at any point you realize, oh my God, this isn't going to work, you're probably right. But I hopefully get to raise some interesting questions and show you how other things can be done in the future, and maybe that'll be interesting. So this is the name of a project I've been working on for a while now, about a year maybe. It spills off of some work that I did at Microsoft beforehand. And the general gist is to try to take some of the good parts of big data ecosystems in terms of the programmability, where people can sit down and approach doing large-scale data analysis without giving up the HPC performance that we, some of us at least, know and love. And hopefully I'll show you by the end of this, if you're not familiar with HPC performance, what it looks like. You can grab everything online. It's delightful. Runs on your laptop, runs on clusters. Yes. So you might have seen these numbers before. If you haven't, this is always a great way to start a talk. These are the numbers that the Berkeley folks put together when evaluating graph processing systems at the most recent OSDI, Operating System Design Implementation Conference, talking about doing 20 iterations of PageRank on a few different popular graph processing systems, 128 cores or so in their system on some graphs that have a few billion edges, right? And they were quite pleased. This is the GraphX paper. So these numbers look good, right? People are doing well. Stuff's a little bit better than Spark. That makes sense because Spark general purpose. Now, all of these things, I said a few billion edges, but a few billion edges is, of course, maybe 10 gigabytes or so. And so my laptop here can do all of that. And it turns out that if you turn on the laptop and you just write about 10 lines of code, you get performance that is outperforming the graph processing thing. There's a few complaints you might have, right? You might say that a few billion edges isn't very big. That might be true, but the systems on the top Spark and graphs start to fall over if you make the graphs any bigger. I'll show you some memory utilization stuff as we go along. You might also say, well, look, we can't all be rocket scientists and write incredibly awesome single-threaded code. So this is the whole program that did that. And this is Rust, by the way. Rust is delightful. We're going to see more Rust as we go on. There's nothing particularly magical about it. So we allocate some memory because we want to play around with some ranks and some degrees of nodes. We get the out degrees of some vertices, and then 20 times we loop through all the nodes and we update the ranks, and we loop through all the edges and increment some weights across edges. That's the whole program, and it's a for loop executed 20 times, and you get performance that's I don't want to call it high performance yet. I mean, this is just sort of, I was hoping this would be a baseline, but so I'm gonna make some friends here. This is my take. A lot of the big data systems at the moment, like it or not, are low performance computing. If they're worse than my laptop, you're using computers not well. And I'm going to try to fix this, or at least we're going to try to take a few steps towards figuring out how can we get a little closer to actually getting towards the machine's capabilities and doing things that are totally amazing and awesome. So the project, Timely Dataflow and Rust, I'm going to walk through what each of these words means or why they're each up here in turn. These are largely non-technical claims I'm going to make. I'm not going to try to convince you of facts, but I'm going to tell you things that are neat and great, and I'm going to try to get you excited about them. Rust is a great new language. It's a lot of fun. It's not Java. It's different. It's definitely lower level, and it has a few appealing properties that have sort of come out of experience that the Rust team has had, writing both performant code, C++ code, but also having to sort of, when they do that, give up some of their high-level abstractions that they really like and really wanted. So it's targeted as a systems programming language, and I think what that means is it's performance sensitive for them. But there are a few cool concepts. Two of them that I want to call attention to are ownership-based resource management. So this is, in contrast with something like C or C++, where you do explicit memory management. You're in charge of allocating, deallocating, paying attention to whether memory is valid or not. That's hard. You have automatic memory management in something like Java, where you have garbage collection, and the system takes care of it for you, but you don't really get to help it out and make it quite clear. Now's a good time to do something on it. Ownership-based memory management is delightful, and it makes a lot of sense. If I have some memory, I'm the unique owner. When I go away, the memory goes away. It's like unique pointers in C++ if you've started to use those. Very pleasant. You get the look and feel of the garbage collected languages without actually having a tracing garbage collector, and that's a really important thing for performance to have, especially in distributed systems where different machines go and garbage collect whenever they want. And it's madness, basically. The other cool thing that I like to call attention to is the idea of zero-cost abstractions, which you also see in C++. But these are high-level concepts, useful high-level concepts like iterators, closures, so these nice little anonymous functions or lambdas that you use all the time, hopefully. They all have the nice property they compile down basically to the code you would have written by hand if you were to go and manually inline everything. So they're not put on the other side of virtual function pointers or anything like that. Everything just works out more or less exactly like you'd expect. Like you'd hope, let's say. So in my experience, it's been really nice. It's giving you the look and feel of a high-level language with the performance of C, which is great. This project, this timely data flow thing, I've written basically by myself. Some folks have checked in some stuff and been helpful in that respect, but you can really put together a performance big data system by yourself in something like this without going insane, which is really cool. Good. Dataflow. So many of us may already know about Dataflow. I just want to point out a few important salient things because I think they connect nicely. So Dataflow is this model, computational model based on directed graphs where you have vertices which correspond to computation and state, arguably, and the edges which correspond to communication. So on the edges, if we're thinking about PageRank again, maybe, we have bits of data that flow around like node and rank, announcing, oh, I'm a node, here's my PageRank. And they move around between bits of the data flow graph, and as they land at particular places in the data flow graph, computation happens. Right? So you indicate at various bits of the graph. Here's some logic, and this logic just says roughly every time some node and rank shows up, I want to look at the edges associated with that node, maybe scale the rank by the degree, and ship the result to all of my downstream neighbors, which is sort of what happens in PageRank. And other things can happen. A little bit further on, we have an aggregation that says, let me add things up, and I've just written, add them up in place. This is great because that's what I want to do. And when I'm all done, maybe I'll put together all of the outputs and in aggregate form. So this isn't meant to be wildly complicated, but there are a few salient points here. It's a different way of writing programs, right, than you're used to. You're used to writing that for loop that I wrote before looks different than this. It's a little maybe weird and uncomfortable. But when you restructure your computation in this data-driven model, you get a lot of really nice properties with respect to parallelism, in particular, since the data moving around is what gets things running, and this is the way that different parts of the program communicate. We can put a lot of different parts of the computation on different workers, different machines, and still get the computation to compute the same thing we were hoping. I personally find that this dovetails really nicely with Rust's notions of ownership, in that moving data around, in Rust at least, there's a very clear contract. When I hand you some data, you get all of the resources proceed other than the passage of time. Right? There are logical ways that computations can proceed. You can have loops, for example, that's going to be a big one. As things go around loops, this is the computation proceeding, and operators in a data flow graph want to know about these sorts of things. Let me show you a horrible picture. Actually, I think it's great, but this is a real data flow graph that timely data flow that uses. This is for computing strongly connected components in real time from a stream of input edges. And if you look at it just briefly, before you turn away, there's all sorts of loops going on. There's a stream of edges coming in, so we have times, like actual wall clock times on records, but then we have loops. This loop here that implicitly we want to know is this the first time around, second time around, third time around. We have, within each of these loops, dangling off of them two independent subcomputations that themselves have loops. So we have nested loops going on. And it's very important to understand, as you're moving data around, what particular iteration of each of these computations does particular piece of data correspond to, so that the operators can make appropriately informed decisions. And if you think for a little bit about, okay, well, how would this get executed on something like, let's say, Spark or Hadoop, where each of these stages is go chat with the central controller, have it spin something up, and come back, and if we do 100 outer iterations here and 100 inner iterations here, this is an enormous number of things. The goal that we have with timely data flow is to take all of this crazy controlled information, where in the computation is a particular piece of data, what sort of progress are we making through the computation, and take it off of the critical path in some sense. So when we have this platform timely, we actually have underneath that two things that are separate. This data plane, high throughput, low latency data plane, which a lot of us hopefully are familiar with things like Hadoop and Spark, or high throughput and things we've linked with low latency. But separate out the control plane, which we don't want to be a consequence of the order in which we scheduled work. And you can see something like Blink. They have control information independent from the scheduler telling people to run. We're going to do that, but to sort of the nth degree. The amount of concurrency that the system is going to have, so the amount of different points in the computation that we can talk about progress in, goes up substantially. We're actually able to move between operations, basically reschedule bits of work at about the 1 microsecond granularity. So this is really cool. And the main thing that it does for me, at least, is it starts to revive the idea of algorithm design. Right? So a lot of people think about what sort of algorithms do we use. In big data, a lot of them look like word count. Or let's take some vectors and we'll compute an outer product and add everything up. This is sort of the algorithm. And at that point, maybe we go and we do some complicated local bit of work, but for everyone here who got an undergraduate computer science education, you learned about all these really cool algorithms that do really neat things, right? These graph algorithms that explore the graphs in certain ways, and network flow and things like this. That you try to actually write them down. You put some loops in, you put some conditional statements. These would be important, but they're difficult to do if every time you make a control decision, you have to eat half a second or something like that for your cluster to remember what it was you were doing and switch proceeds. There's a bit of a stack. I'm just going to advertise some things on the stack. I'm also going to advertise some of Keynote's awesome transitions here and stuff. So we have Differential, which is a library that I talked about yesterday in the graph processing thing. This is a system for doing essentially automatic incremental computation. I just showed you the context of graphs, but it's a bit more general of that, and gives sub-millisecond latencies for actually fully reevaluating computations on changed data sets, as long as the change is not particularly large. And there's some cool things that we built on top of that. There's a data log layer that, as far as I'm aware, outperforms we gave the term was yesterday, with the industry-leading data log logic blocks, which they said they're delighted for us to say that as long as we're not lying. So there's a really cool click join up here, join star. There's some really amazing work of people, and I just want to tell everyone about this work on worst-case optimal joins. Basically, the way people have been doing joins for the past 40 years is wrong. You can show that they're asymptotically suboptimal, and the reason people spend so much time looking at query optimizers is because they have been doing these binary joins, which is just the wrong way to do joins. And so there's a cool new way that some folks at Buffalo and Stanford put together, and you can totally use it. And it's really cool. You should learn about it because it's awesome if you like learning about things. When we did this at Microsoft, we had a few other components too on top of the C# stack. There's a graph processing library and an asynchronous machine learning library. These could totally be done. I haven't done them mostly because I'm not particularly clear on what needs to be done to make them most relevant for people in the future. But I would totally recommend, if anyone's keen, to drop me a note and we can talk about how to make a high-performance graph processing library on top of this. The C# version was about 500 lines of code, so it's not an epic investment. There are a bunch of cool apps that we can write on top of this. Whatever. There's some cool access control thing on Datalog. Connecting components in BFS, I talked about these a bit yesterday. Motif finding on sort of in the same style as Arabesque yesterday. And you could also, if you like, write against raw timely metal itself, doing something like PageRank, which is what we were talking about at the beginning of the talk. So I'm going to show you that again and try to tell you how awesome, how awesome things can be. So, remember this picture? Right, we used to have single thread down there. I got rid of the single thread thing and wrote a timely computation that I will show you in just a few minutes. And I don't know what people are hoping for here, but these are the numbers. So they're different, right? So you can have a conversation about where the gap is in there. I'd like you to have that conversation with the people who build these systems. I don't need to be involved. Here's a trace, sort of suggesting what's going on. These are the same machines. GraphX running on the top, timely running on the bottom, and you can see a whole bunch of things. First of all, the top is a mess. It goes out to 350 seconds to do the computation, whereas we're about 25 down here. The green line, if you can see it, is memory utilization. This is a data set that is on disk 6 gigabytes in a 1 terabyte environment. So these machines, there's 16 of them, are getting up to about 70% memory utilization for GraphX, and it's about a gig or two for each machine down here. So sort of like you'd expect. And the main reason this happens, let me show you some code, is because when you write timely Dataflow code, it's a lot more like a programming language, I have to admit. So it's not a big data solution that you type .pagerank and PageRank happens. But you get to tell the program what you actually want to have happen. So the whole program here is 70 lines long, some of which is including some stuff here, some of which is there's some stuff about parsing arguments or reading out things. But the place I'd like to point out roughly is in the core of the computation, where you write a vertex that does some thinking. You actually get to say, what do I want to do, right? And you get to write code that looks like this, that says, well, for each of the bits of data that I happen to find and presented to me, I'd like to go to my array, right? Not some weird hash map something, but my array, actually dump the data at a particular location that I've described, and what will happen under the covers is you'll do a memory access, a dereference, and you'll bump the thing and you'll write it back, and that's it. That's what your program says. That's what the compiled code does. No funny business. So if your code that you're writing can actually go quickly, then you should be able to exploit the machine that way. There's nice typed data throughout, but it's all basically a near zero copy API down to the network. It saturates 10 gig links because the serialization is nice and crisp. And except for the fact that you do have to write a little bit of a program in the sense of describe what you want to do, how you want to walk through your set of edges. I find it to be pretty pleasant if you think you need a bit more control. I should be totally clear, this example is not literally the one that gave us the numbers before. This example just takes a whole bunch of edges and puts them in a deck and walks through them in any particular order. You get the numbers from the previous one if you make an optimization, which is to sort the edges by destination. Right? That's interesting. But you get to choose to do that, which is really nice, right? So if you're writing your program, you're like, oh, I'd like to do this just a little bit differently. I'd like to compress the data somehow, or I'd like to change the order or pre-aggregate it. You just have to write the code. You don't have to go and fork your favorite big data project and introduce some privileged operators. So I find it to be a very lightweight way to put together big data computations whose performance can be dramatically better. It's an open question whether this is a delightful way for everyone to be using big data stuff going forward. This is the last slide to remind everyone, timely Dataflow inroad. Tell your friends. I don't have a hashtag yet, but and feel free to hop over here, clone the repo, just get in touch, say howdy, ask any questions. But if there are questions, I'll take those now too.
Any questions?
Yeah, shoot.
Anybody has questions?
errors during the floods?
So the question was about Rust's type system, which is indeed powerful. Does it help you prevent errors? And absolutely yes. Or in my experience, absolutely yes. The ownership-based properties of Rust's type system. So it's very clear about who owns which particular pieces of data, and it helps you, or helps in my mind a lot when you're trying to write a program and you think, "Ooh, excellent! Someone just showed me a bit of data that I got off of the network or something like this. What am I allowed to do to it? Do I own it now? Am I only allowed to look at it?" One really cool example, by the way, is the serialization that Rust does, that Timely does underneath the covers in Rust. Starts by, if you're trying to receive a type T, it starts by showing you, in Rust terms, a reference to T. This is like a pointer to a T, but one that you're not allowed to mutate. And that's really cool because it can actually do this without allocating the data itself. So if you wanted to look at a whole bunch of strings that go by, there's no strings that are actually allocated. They're all big hunks of binary memory where some pointers are tweaked internally. If you want to call phone on this and make it your own phone copy, you absolutely can. But because Rust distinguishes between these two things, we can actually get some pretty good performance if we know that you're not allowed to mutate the data, for example. Rust's type system so far for me has been delightful. It remains unclear whether it's delightful for people one level up in the stack, if it's just that I've been able to tie everyone's hands very thoroughly, and I'm very satisfied with that.
Right. Does it have support for high availability?
Absolutely not. Sorry, the question is high availability. No, absolutely not. So I have like three answers to this. One of them is very flip. One of them, so the honest answer is no, it does not. The flip answer is, in the past year, it has never crashed in a recoverable way. Right? So there have been bugs for sure, but nothing that would have caused something to go down and come back up again. My experience with this, one of the reasons it doesn't have high availability yet is I don't actually know the main source of failures that people need to deal with in the wild. My experience hasn't been that NICs are flaky or anything like that. My experience has been that people use the JVM, and the JVM goes out of memory because the pictures we saw before. Shutting down your process and restarting it is a great form of garbage collection. So fault tolerance. So, and these are all very, very flip sorts of things. From my point of view, if you can get your job done in about 15 seconds instead of 5 minutes, this is really good. This isn't a great answer if you're a bank and you want something to actually work all the time. So I'm not pushing this as, look, everyone should just get rid of their big data solutions, so much as we can think of things a little bit differently. Another point, though I didn't really talk about it too much here, this differential layer, for example, that lives on top, is one level up, and it has much more clear deterministic semantics about what outputs you're supposed to see. So replay is absolutely an option in that sort of setting. The lower level gunk here, Timely Dataflow in Rust particularly, is much more about moving data around. And in my opinion, may not be the right place to introduce high availability. So these sorts of questions being still open, I haven't tried to go and bake something in. So it's sort of yes, sort of no, mostly no.
Any more questions?
How much data were you processing on that example?
So how much data was I processing? This is the graph processing thing. Yeah, so this is about, it's a little hard. So it depends how you represent the data. And I know how to represent the data well. For me, it was about 15 gigabytes of data. 20 iterations, so the 300 gigabytes shuffled around. You can do the math and ask, if you have a 10 gigabit NIC, what should you be getting? And I think this is a great thing to do, is to think about what should I be getting and figure out how close are you to done. We were saturating the NICs, basically, and that more or less drove how long it took our computation.
Okay, so we're done. Thank you so much.